Section 1.5, Measurement Uncertainty, Accuracy, and Precision. By the end of this section, you will be able to 1. Define accuracy and precision. 2. Distinguish exact and uncertain numbers. 3. Correctly represent uncertainty in quantities using significant figures. 4. Apply proper rounding rules to computed quantities. Counting is the only type of measurement that is free from uncertainty, provided the number of objects being counted does not change while the counting process is underway. The result of such a counting measurement is an example of an exact number. By counting the eggs in a carton, one can determine exactly how many eggs the carton contains. The numbers of defined quantities are also exact. By definition, 1 foot is exactly 12 inches, 1 inch is exactly 2.54 centimeters, and 1 gram is exactly 0.001 kilogram. Quantities derived from measurements other than counting, however, are uncertain to varying extents due to practical limitations of the measurement process used. 1.5.1 Significant figures in measurement. The numbers of measured quantities, unlike defined or directly counted quantities, are not exact. To measure the volume of liquid in a graduated cylinder, you should make a reading at the bottom of the meniscus, the lowest point on the curved surface of the liquid. Figure 1.26. 20. Make reading here. To measure the volume of liquid in this graduated cylinder, you must mentally subdivide the distance between the 21 and 22 milliliter marks into tenths of a milliliter, and then make a reading, estimate, at the bottom of the meniscus. Refer to the illustration in Figure 1.26. The bottom of the meniscus in this case clearly lies between the 21 and 22 markings, meaning the liquid volume is certainly greater than 21 milliliter but less than 22 milliliter. The meniscus appears to be a bit closer to the 22 milliliter mark than to the 21 milliliter mark, and so a reasonable estimate of the liquid's volume would be 21.6 milliliter. In the number 21.6, then, the digits 2 and 1 are certain, but the 6 is an estimate. Some people might estimate the meniscus position to be equally distant from each of the markings and estimate the 10th place digit as 5, while others may think it to be even closer to the 22 milliliter mark and estimate this digit to be 7. Note that it would be pointless to attempt to estimate a digit for the hundredths place, given that the 10th place digit is uncertain. In general, numerical scales such as the one on this graduated cylinder will permit measurements to 1/10 of the smallest scale division. The scale in this case has 1 milliliter divisions, and so volumes may be measured to the nearest 0.1 milliliter. This concept holds true for all measurements, even if you do not actively make an estimate. If you place a quarter on a standard electronic balance, you may obtain a reading of 6.72 gram. The digits 6 and 7 are certain, and the 2 indicates that the mass of the quarter is likely between 6.71 and 6.73 grams. The quarter weighs about 6.72 grams, with a nominal uncertainty in the measurement of plus or minus 0.01 gram. If the coin is weighed on a more sensitive balance, the mass might be 6.723 gram. This means its mass lies between 6.722 and 6.724 grams, an uncertainty of 0.001 gram. Every measurement has some uncertainty, which depends on the device used and the user's ability. All of the digits in a measurement, including the uncertain last digit, are called significant figures or significant digits. Note that 0 may be a measured value. For example, if you stand on a scale that shows weight to the nearest pound and it shows 120, then the 1, hundreds, 2, tens, and 0, ones, are all significant, measured, values. A measurement result is properly reported when its significant digits accurately represent the certainty of the measurement process. But what if you were analyzing a reported value and trying to determine what is significant and what is not? Well, for starters, all non-zero digits are significant, and it is only zeros that require some thought. We will use the terms leading, trailing, and captive for the zeros and will consider how to deal with them. Figure A. 3090, captive, trailing. B. 0.008020, leading, captive, trailing. Starting with the first non-zero digit on the left, count this digit and all remaining digits to the right. This is the number of significant figures in the measurement unless the last digit is a trailing zero lying to the left of the decimal point. Figure A. 1267 meter. First non-zero figure on the left. 4 significant figures. B. 55.0 gram. First non-zero figure on the left. 3 significant figures. Note that the zero is to the right of the decimal point and therefore a significant figure. Captive zeros result from measurement and are therefore always significant. Leading zeros, however, are never significant, they merely tell us where the decimal point is located. Figure A. 70.607 milliliter. First non-zero figure on the left. 5 significant figures. All figures are measured including the 2 zeros. B. 0.00832407 milliliter. First non-zero figure on the left. 6 significant figures. The leading zeros in this example are not significant. We could use exponential notation, as described in Appendix B, and express the number as 8.32407, multiplied by 10 to the power of negative 3. Then the number 8.32407 contains all of the significant figures, and 10 to the power of negative 3 locates the decimal point. The number of significant figures is uncertain in a number that ends with a zero to the left of the decimal point location. The zeros in the measurement 1,300 grams could be significant or they could simply indicate where the decimal point is located. The ambiguity can be resolved with the use of exponential notation. 1.3 multiplied by 10 to the power of 3, 2 significant figures. 1.30 multiplied by 10 to the power of 3, 3 significant figures, if the tens place was measured. Or 1.300 multiplied by 10 to the power of 3, 4 significant figures, if the ones place was also measured. In cases where only the decimal formatted number is available, it is prudent to assume that all trailing zeros are not significant. Figure 1300 gram. Significant figures, clearly result of measurement. These zeros could be significant, measured, or they could be placeholders. When determining significant figures, be sure to pay attention to reported values and think about the measurement and significant figures in terms of what is reasonable or likely when evaluating whether the value makes sense. For example, the official January 2014 census reported the resident population of the U.S. as 317,297,725. Do you think the U.S. population was correctly determined to the reported 9 significant figures, that is, to the exact number of people? People are constantly being born, dying, or moving into or out of the country, and assumptions are made to account for the large number of people who are not actually counted. Because of these uncertainties, it might be more reasonable to expect that we know the population to within perhaps a million or so, in which case the population should be reported as 3.17, multiplied by 10 to the power of 8 people. 1.5.2. Significant figures in calculations. A second important principle of uncertainty is that results calculated from a measurement are at least as uncertain as the measurement itself. Take the uncertainty in measurements into account to avoid misrepresenting the uncertainty in calculated results. One way to do this is to report the result of a calculation with the correct number of significant figures, which is determined by the following 3 rules for rounding numbers. 1. When adding or subtracting numbers, round the result to the same number of decimal places as the number with the least number of decimal places, the least certain value in terms of addition and subtraction. 2. When multiplying or dividing numbers, round the result to the same number of digits as the number with the least number of significant figures, the least certain value in terms of multiplication and division. 3. If the digit to be dropped, the one immediately to the right of the digit to be retained, is less than 5, round down, and leave the retained digit unchanged. If it is more than 5, round up, and increase the retained digit by 1. If the dropped digit is 5, round up or down, whichever yields an even value for the retained digit. The last part of this rule may strike you as a bit odd, but it's based on reliable statistics and is aimed at avoiding any bias when dropping the digit 5, since it is equally close to both possible values of the retained digit. The following examples illustrate the application of this rule in rounding a few different numbers to three significant figures. 1. 0.028675 rounds up to 0.0287. The drop digit, 7, is greater than 5. 2. 18.3384 rounds down to 18.3. The drop digit, 3, is less than 5. 3. 6.8752 rounds up to 6.88. The drop digit is 5, and the retained digit is even. 4. 92.85 rounds down to 92.8. The drop digit is 5, and the retained digit is even. Let's work through these rules with a few examples. Example 1.3. Rounding numbers. Round the following to the indicated number of significant figures. A. 31.57, to two significant figures. B. 8.1649, to three significant figures. C. 0.051065, to four significant figures. D. 0.90275, to four significant figures. Solution. A. 31.57 rounds up to 32. The drop digit is 5, and the retained digit is even. B. 8.1649 rounds down to 8.16. The drop digit, 4, is less than 5. C. 0.051065 rounds down to 0.05106. The drop digit is 5, and the retained digit is even. D. 0.90275 rounds up to 0.9028. The drop digit is 5, and the retained digit is even. Check your learning. Round the following to the indicated number of significant figures. A. 0.424, to two significant figures. B. 0.0038661, to three significant figures. C. 421.25, to four significant figures. D. 28,683.5, to five significant figures. Answer. A. 0.42. B. 0.00387. C. 421.2. D. 28,684. Example 1.4. Addition and subtraction with significant figures. Rule. When adding or subtracting numbers, round the result to the same number of decimal places as the number with the fewest decimal places, i.e., the least certain value in terms of addition and subtraction. A. Add 1.0023 gram and 4.383 gram. B. Subtract 421.23 gram from 486 gram. Solution. A. 1.0023 gram plus 4.383 gram equals 5.3853 gram. Answer is 5.385 gram, round to the thousandths place, 3 decimal places. B. 486 gram minus 421.23 gram equals 64.77 gram. Answer is 65 gram, round to the ones place, no decimal places. Figure A. 1.0023, 3 ten-thousandths place. Plus 4.383 thousandths place, least precise. Equals 5.3853. Round to thousandths. Figure B. 486 gram minus 421.23 gram equals 64.77 gram. Round to ones. Answer is 65 gram. Check your learning. A. Add 2.334 milliliter and 0.31 milliliter. B. Subtract 55.8752 meter from 56.533 meter. Answer. A. 2.64 milliliter. B. 0.658 meter. Example 1.5. Multiplication and division with significant figures. Rule. When multiplying or dividing numbers, Round the result to the same number of digits as the number with the fewest significant figures, the least certain value in terms of multiplication and division. A. Multiply 0.6238 cm by 6.6 cm. B. Divide 421.23 gram by 486 milliliter. Solution. A. 0.6238 cm multiplied by 6.6 cm equals 4.11708 cm squared. The result is 4.1 cm squared, round to two significant figures. 4 significant figures multiplied by 2 significant figures produces 2 significant figures answer. B. 421.23 gram divided by 486 milliliter equals 0.86728 gram per milliliter. The result is 0.867 gram per milliliter, round to 3 significant figures. 5 significant figures divided by 3 significant figures produces 3 significant figures answer. Check your learning. A. Multiply 2.334 cm and 0.320 cm. B. Divide 55.8752 meter by 56.53 second. Answer. A. 0.747 cm squared. B. 0.9884 meter per second. In the midst of all these technicalities, it is important to keep in mind the reason for these rules about significant figures and rounding, to correctly represent the certainty of the values reported, and to ensure that a calculated result is not represented as being more certain than the least certain value used in the calculation. Example 1.6. Calculation with significant figures. One common bathtub is 13.44 decimeter long, 5.920 decimeter wide, and 2.54 decimeter deep. Assume that the tub is rectangular and calculate its approximate volume in liters. Solution. V equals L multiplied by W multiplied by D equals 13.44 decimeter multiplied by 5.920 decimeter multiplied by 2.54 decimeter equals 202.09459 decimeter cubed. Value from calculator equals 202 decimeter cubed, or 202 liter. Answer rounded to 3 significant figures. Check your learning. What is the density of a liquid with a mass of 31.1415 gram and a volume of 30.13 centimeter cubed? Answer. 1.034 gram per milliliter. Example 1.7. Experimental determination of density using water displacement. A piece of rebar is weighed and then submerged in a graduated cylinder partially filled with water, with results as shown. Figure. Rebar mass equals 69.658 gram. Final volume equals 22.4 milliliter. Initial volume equals 13.5 milliliter. A. Use these values to determine the density of this piece of rebar. B. Rebar is mostly iron. Does your result in A support this statement? How? Solution. The volume of the piece of rebar is equal to the volume of the water displaced. Volume equals 22.4 milliliter minus 13.5 milliliter equals 8.9 milliliter equals 8.9 centimeter cubed. Rounded to the nearest 0.1 milliliter per the rule for addition and subtraction. The density is the mass to volume ratio. Density equals mass divided by volume equals 69.658 gram divided by 8.9 centimeter cubed equals 7.8 gram per centimeter cubed. Rounded to 2 significant figures per the rule for multiplication and division. From table 1.4, the density of iron is 7.9 gram per centimeter cubed, very close to that of rebar, which lends some support to the fact that rebar is mostly iron. Check your learning. An irregularly shaped piece of a shiny yellowish material is weighed and then submerged in a graduated cylinder, with results as shown. Figure. Mass equals 51.842 gram. Final volume equals 19.8 milliliter. Initial volume equals 17.1 milliliter. A. Use these values to determine the density of this material. B. Do you have any reasonable guesses as to the identity of this material? Explain your reasoning. Answer. A. 19 gram per centimeter cubed. B. It is likely gold. The right appearance for gold and very close to the density given for gold in Table 1.4. 1.5.3. Accuracy and precision. Scientists typically make repeated measurements of a quantity to ensure the quality of their findings and to evaluate both the precision and the accuracy of their results. Measurements are said to be precise if they yield very similar results when repeated in the same manner. A measurement is considered accurate if it yields a result that is very close to the true or accepted value. Precise values agree with each other. Accurate values agree with a true value. These characterizations can be extended to other contexts, such as the results of an archery competition. Figure 1.27. Figure 1.27. A. Accurate and precise. B. Precise, not accurate. C. Not accurate, not precise. Figure 1.27. A. These arrows are close to both the bull's eye and one another, so they are both accurate and precise. B. These arrows are close to one another but not on target, so they are precise but not accurate. C. These arrows are neither on target nor close to one another, so they are neither accurate nor precise. Suppose a quality control chemist at a pharmaceutical company is tasked with checking the accuracy and precision of 3 different machines that are meant to dispense 10 ounces, 296 milliliter, of cough syrup into storage bottles. She proceeds to use each machine to fill 5 bottles and then carefully determines the actual volume dispensed, obtaining the results tabulated in Table 1.5. Table 1.5. Volume, milliliter, of cough medicine delivered by 10-ounce, 296 milliliter, dispensers. Dispenser number 1, 283.3, 284.1, 283.9, 284.0, 284.1. Dispenser number 2, 298.3, 294.2, 296.0, 297.8, 293.9. Dispenser number 3, 296.1, 295.9, 296.1, 296.0, 296.1. Considering these results, she will report that dispenser number 1 is precise, values all close to one another, within a few tenths of a milliliter, but not accurate. None of the values are close to the target value of 296 milliliter, each being more than 10 milliliter too low. Results for dispenser number 2 represent improved accuracy. Each volume is less than 3 milliliter away from 296 milliliter. But worse precision. Volumes vary by more than 4 milliliter. Finally, she can report that dispenser number 3 is working well, dispensing cough syrup both accurately, all volumes within 0.1 milliliter of the target volume, and precisely, volumes differing from each other by no more than 0.2 milliliter.